Well, it's time. Welcome back, everyone. For today's class, we're just moving forward through example or section 2.3. We really only just started it at the very last part of class on Tuesday. We finished off section 2.2, so the due date on that assignment, June 18th, is considered official. But I moved this due date back a day since we're taking an extra day to complete the section. Our very first assignment, section 2.1, is due today. And as far as the grading goes, I try to grade as soon as possible. So if you handed this in early, I probably already graded it early, and you can find your feedback on Canvas. And at any point, you can click here to check how your grades are going. If anything seems like it's missing, anything along those lines, don't hesitate to reach out and we'll get it corrected right away. But that's our goal for today. Work through section 2.3, the limit laws. Then we're going to skip to section 2.5 towards the last part of the day and take a look into continuity. But any questions or comments at all to start us out, folks? Okay, well, to start us off, I think it's a good idea to do a bit of a refresher before we jump into section 2.3. The purpose of section 2.2 is to give us a conceptual view of what the limit of a function looks like when we consider it through graphs. When we look into the limit of a function, but we want to say compute the limits algebraically, maybe in a problem like this one, or in a problem like the example 2 below, and so on, we need a few more tools because a graph isn't always provided. In fact, we have three functions here, f of x, g of x, and h of x, and no information whatsoever is provided through a graph. Yet we want to compute these three different kinds of limits, different combinations of these functions, other algebraic expressions like x squared. And so this is where the limit laws up above start to come into play. So we're going to be using these as tools to compute the limits as efficiently as possible. It really came in four different kinds of blocks. Block one, limit laws 1 through 5, are different ways to combine functions, whether we're adding, subtracting, multiplying, dividing them, or taking a constant multiple of them, like in part 3. Then the next block, 6 through 11, these are just different algebraic properties that we can use to evaluate limits as fast as possible. So these give us dead-on answers to certain limits. If we're taking the limit of a constant, then it just produces the constant, and so on. We mentioned that part 12 is just inherited over from section 2.2. This gives us conditions on when a limit exists. A limit exists if and only if the left-hand limit and the right-hand limit both exist. And finally, we have a couple more rules, 13 and 14, that we're going to investigate a little bit further as we get deeper into the notes. So we'll come back to those limits. But this is where we ended last class, just kind of a wall of text on different limit laws. If you can kind of chunk these in ways that make sense to group them, that's a great way to organize. And also, if this feels kind of overwhelming, we mentioned the purpose of these is the more we practice, the more they become second nature. Any questions at all, folks, with the limit laws at the moment? Okay, my next two examples really are just a way to kind of get into these laws to see how they work. Example one, you'll be doing something similar in the homework through two different graphs. Here, I just have three provided limits. It says that given that the limit of f of x as x tends towards 2 is 4, the limit of g of x as x tends towards 2 is -2, and the limit of h of x as x tends towards 2 once again is 0, find the limits that exist amongst this list here. If the limit doesn't exist, we'll also explain why. And really the whole purpose of example 1 again is just to review these limit laws. So on part A, the way we would probably break this one down is involve limit law number 2. Limit law number 2 says if you're subtracting two different limits, one function here and a constant multiple of a whole other function, you can just split this in two. So using that limit law, we can rewrite this as equals limit as x tends towards 2 of the first function f of x minus the limit as x tends towards 2 of the second function, but the second function is the entirety 3 times g of x. So when we use the limit law number 2 right here, we're not using exactly g of x in that position where this g of x was. We're using -3 times g of x. That is a bona fide function in its own right. So we're allowed to swap where the g of x is down here for a constant multiple, 3 times g of x. So that's our first limit law used. Any questions at the moment? Okay, and for the sake of a paper trail to explain what we used and why, I'll use this abbreviation like last class, LL to stand for limit law, referring to this this list right here, and 1 just to say we use limit law, actually we use limit law 2. Let me fix that. So first step is by limit law 2. And now we can make an evaluation on this one. We were given that the limit as x tends towards 2 of f of x is 4, so we can just make that substitution here right now. That value comes out as a 4 minus. Now for the next portion here, we have 3 times g of x. We can't necessarily use this just yet if we're using the limit laws really carefully. What we need is limit law number 3. C is a constant. It could be 5. It could be, say, 3, like in this problem. We have a limit of 3 times a function. That constant can move out in front. So all we're going to do is take 3, move it in front of the limit. So it'll go right here. So this becomes 3 times the limit as x tends towards 2 of g of x. And I forgot already what limit law that one was. That one is by limit law 3. So now that we've used limit law number 2, limit law number 3, to first split the difference, then to rearrange the constant multiple, 3 times g of x, we can now just make a big substitution right here. All of our limit laws are over at this step. So in place of where it's highlighted here in green, we can now just substitute in a -2, and it's all arithmetic from here. Any questions or comments at all, folks, following the process? Okay, let's put in our value. This becomes 4 minus 3 times -2, making that final substitution for where this limit was. That one's not a limit law, just ordinary mathematics, but substitution. So this becomes 4 plus 6 for a value of 10. Then the work is complete entirely on that one there. What this is saying is the new function f of x minus 3 times g of x is getting closer and closer to a value of 10, as close to 10 as you would like, as the input gets closer and closer to the number 2. So we'll try it again and a couple more trickier problems. But this is pretty much par for the course on this section 2.3, using these limit laws. Here we're using them very, very carefully because they're brand new. But as we get further along in this section, we'll show how to do this work maybe a bit more efficiently in some longer problems. Any questions or comments so far? Okay, well, let's try this out again. This time we're taking the limit x tends towards 2. And we have 2 functions, really. We have a function x squared that goes here. We have some other function, let me change the color, square root of f of x. It's a composition of functions that goes here. But because they're being multiplied, we can think of it in terms of these. The name f of x and g of x are irrelevant. They could have been any variable name. The functions could have been u and v, or even x and y as functions. So we're thinking in place of this f of x that we see in limit law number 4 as being x squared. G of x in limit law number 4 is the entire composition of functions, square root f of x. And limit law number 4 can be used in this way. the limit of product of functions is the product of the limit of functions. So we're going to split in that kind of way. So here's what it looks like in practice when we write it out. This becomes the limit as x tends towards 2 of x squared times the limit as x tends towards 2 of the composition square root f of x. This is by limit law. I already forgot, let me double check. Limit law number 4, LL4. So that's the first limit law down. We can't evaluate any of these limits directly based off these 3 highlighted pieces of information given. But if we scroll down a little bit further into the next block of limit laws, 6 through 11, we have a lot of powerful tools here. In particular, limit law number 9 is fantastic. It says take any power function, x raised to a power n. If x is heading towards a, you just swap, directly substitute in a for x. So by limit law number 9, all we're doing is taking that 2, dropping it in for x, and squaring it. So it's a direct substitution property, giving us 2 to the power of 2, and this is by limit law 9. So take another look at that. Limit law number 9 is in this form. The power of n is power 2. So if x is heading towards 2, x squared is just heading towards, well, 2 squared, because that's where x itself is going. So we can't always directly substitute in this way. We'll find plenty of examples where it doesn't work. But this is one case where all we had to do is just drop in the number. Now we have to resolve this other factor here. Limit as x tends towards 2 of square root f of x. But any questions on what we did with x squared? Okay, excuse me. The next limit law we can use, we skip all the way down to say limit law number 11, where we take an nth root. Here, n is a positive integer, so n is allowed to be 2, for example. That's what the implied index is for this square root. So if it's a square root, n is 2, we usually drop it. The limit as x tends towards a of the square root of a function becomes this. It's just the square root of the limit of the function itself. So in other words, the limit operator can commute inside the square root operator or the cube root and so on. So this becomes square root limit as x tends towards 2 of f of x. And this part is by limit law 11. Once we get here, it's all algebra from this point. We can make a substitution because we know exactly what that limit is. Comes out as a 4. This part's 4 as well. So we're just about done at this stage. Any questions, folks, with any of those 3 different limit laws we used this time? Okay, well, let's make our substitution. We used limit law number 11, so we could use the given information that limit for f of x as x tends towards 2 is 4 can be used right at this stage. We're just going to substitute in a 4 there. So this becomes a 4 from the 2 squared part times the square root of 4. That's our substitution following the color coding. So the root of 4 is 2. This becomes just 4 times 2. 4 and 8 altogether. Then at that stage, the problem is completely over. So one last one to take a look into. We have g of x divided by h of x. We haven't used every single limit law, but we'll use more and more as we get through these notes in section 2.2. If you see a function like part C, g of x divided by h of x, the limit law you definitely would want to use is limit law number 5. And again, the names of the functions, f and g, are irrelevant. It just has to be one function divided by some other function, possibly the same function as well. So whether it's g and h, a pattern is the most important thing. We can take the limit of a quotient and rewrite it as the quotient of the limits. Hello. So this becomes altogether the limit as x tends towards 2 of g of x divided by the limit as x tends towards 2 of h of x. So that's the good use of our limit law number 5 on this one. Again, that's pretty much the only limit law we had to use on this one. It looks like part B was maybe the harder problem on the list. We used 3 different limit laws to get through it. But any questions at all, folks, using that limit law 5? Okay, well, now that we've used the limit law 5, you might notice that there's kind of an issue here. Sure, we can substitute in a value for g of x. That's -2 in the numerator, so no big deal. It says that this limit law only works if g of x is not equal to 0, but the names of the functions aren't as relevant as the pattern. When it says g here on the limit laws, it's referring to the denominator function. Our particular denominator function is h of x, and they provide information said the limit of h of x as x tends towards 2 is in fact 0. So this limit law actually fails for us. We can't use this whatsoever, and so we here would say this limit does not exist, or just a D and E altogether. Now, it's possible that more could go on with this problem. If we knew what was going on with g of x, and we know what's going on with h of x, more could happen. But from the very limited information we were given on this problem, this would be the best answer that we could provide, that the limit doesn't exist. In other words, we cannot use this limit law whatsoever. We're pretty much just stuck on the way this problem was started. Well, that's the first initial tour through the different limit laws. We're going to run through them all again in the next problem. But any questions first, folks, with this initial example 1? Okay, again, it's kind of a weird problem because we don't have a graph for f. We've been using graphs quite a lot. We don't even have an equation. We just have one tiny bit of information, same for g, same for h. We know the limit at one value. So it's kind of a strange problem. The major goal is just to use the limit laws in particular. So maybe a more interesting problem would be something like this one here on example 2. This time, we know what the function is, 2x plus 8 divided by the square root of 4x plus 1. Here, these instructions are pretty specific. Evaluate the limit, justify each step by indicating the appropriate limit laws. I want to mention, we're not going to do this on every single problem. We're only going to do this once on example 2, and the whole purpose of this is just for practicing the limit laws. How to look them up, determine which one is relevant, and we'll cite them in the problem like we're doing on the last exercises as well. So not on every single example are we going to break it down as much as this one. It's really just for us to kind of, once again, digest all this information, properties 1 through 14. So let's go slowly. There's lots going on in this limit. We have a 2x plus 8 divided by 4x plus 1. One property that we've been looking into are properties like these, where we can sometimes just directly substitute in a value. The power function allows that to work. That happens to be a polynomial. And property number 14, this is in red because I misspelled it on the first run through. That's the correct spelling of substitution. It says if the function is a polynomial or a rational function and a is in the domain, then the limit of that function, polynomial or rational, is found by just taking a, plugging it right in. However, this is not a polynomial because of the denominator there. It's also not a rational function because of the square root symbol that's provided right here. So if that square root symbol was gone, we could just plug in the number 2 and be done. So the direct substitution property cannot be used just yet, but we will use it as we break down this limit further and further. First thing we want to do is, let's go and use limit law number 5 one more time. We can split this up as numerator versus denominator, hoping that this doesn't occur again on this problem. It will on the others later on in the notes. So starting off by limit law number 5, we can say this is equal to a numerator, limit as x tends towards 2, of 2x plus 8. That entire function, divide by the denominator, limit as x tends towards 2, of the composition function, square root, 4x plus 1. And this is by limit law 5. Let me double check the numbering there. Yeah, limit law 5. So it's really just a strategy of divide and conquer. If there's lots going on, see what happens in the numerator, see what happens in the denominator. But now that we've split it up in this way, let's review what we mean when we say polynomial. Polynomial are things along the lines of, say, x. That's a degree 1 polynomial, x power n or x power 3 and so on. Those are power functions, but those would be polynomials as well. This is an nth degree polynomial, x power n. So if the function's a polynomial, and that one's a polynomial, it's degree 1 linear, the direct substitution property says all you need to do to evaluate this limit is take wherever x is heading towards, plug it in for what x is. So we're just going to plug in the value of 2 in for x. So take this entire thing, x tending towards 2, plug it in for x. This is our amazing property number 14, direct substitution. So we'll call this a step of limit law 14. So the numerator looks like it's totally done. We just get 2 times 2, follow the color coding for the substitution. 2 came from that particular limit, plus 8. And this is by limit law 14, the so-called direct substitution property. This property is so nice for valuing limits because it takes the process of doing a limit and makes it just a function evaluation. It's so nice that the entire next section we'll cover, 2.5, is all about this. We'll later on call this a property of continuity and investigate the class of functions that are continuous. So the limit just becomes that whole process, throw in the number. But then it leaves the denominator. The denominator leaves a little bit more to be desired because it's not a polynomial once you throw a square root symbol on it. So we need a different limit law to resolve that. But that's just limit law number 11 again, like we used on the prior example. Here, if it's just a square root symbol, n is implied to be 2, we just have to hope that the limit is positive so we don't get anything complex valued. That would come out as positive, looks like when we do the limit. And so limit law 11 says for the punchline, the limit on the outside commutes inside the root, the square root for this example. So we can rewrite this whole thing as a more gigantic looking square root of the limit as x tends towards 2 of the function 4x plus 1. I think that was limit law 11. So limit law 11 used once again. Gives us that as a result. And I know we're kind of just on our way on this one at this point. I put in a lot of white space, but it doesn't look like we're going to use a whole lot of it overall. Let's maybe drop down a line. Any questions at all, folks, getting to this stage? Okay, well, on the next step, we said we could use limit law 14 on this thing because it's a degree 1 polynomial. But the same idea right here. That's a degree 1 polynomial as well. So by the direct substitution property, limit law 14, we can just take x tending towards 2, plug it in for that x. So in the numerator, we're just doing arithmetic, 4 plus 8 for a value of 12. In the denominator, easiest mistake to make is to forget the square root symbol because we're fixating on the limit itself. But we're throwing in 4 times the value for x, which is 2 plus 1. So this is limit law 14 once again. At this stage, we're just doing arithmetic all the way out to complete the problem. Logan asks, why is it limit law 11 instead of 10, since there's no f in the f of x? Let me double check that. So we look at limit law 10 versus limit law 11. Oh, I see what you're saying. That's a great comment. So limit law 10 would be specifically if what you see right here is nothing but x. It can't have the 4 times x. It can't have the plus 1. Limit law 10 requires just x and nothing else whatsoever. But that doesn't fully answer your question because also you have observed limit law 11 requires there to be an f of x. We have a 4x plus 1, so we could really visualize this by limit law 11 if we did this little switcheroo by a substitution. Let's place limit law 11 here to really focus on it. And I want to highlight just this part right here. So when we go to analyze just that denominator, limit as x tends towards 2 of the square root 4x plus 1. Like you mentioned, this is a great point on the calculus or the algebra of this entire thing and making the substitution. Limit law 11 says there has to be an f of x, but the f of x could be any function whose limit exists. That was the only requirement on the top of the limit laws, is that the limit of f of x exists. Same for g of x. But it's any function whatsoever. That means when you see a f of x here, when you go to use limit law number 11, you get to say what f of x is. F of x is, for our purposes, 4x plus 1. So this just becomes limit as x tends towards 2 of the square root of f of x. Once we go to make that substitution, then limit law 11 is fully in force. We have it looking identical here on paper versus the law on the top of the section. This becomes a square root, limit x tends towards 2 of f of x. But then when we want to actually compute that thing, we unpack what f of x is. We put in square root, limit x tends towards 2 of 4x plus 1. So this is the long form answer to the question, but really the short answer is f of x is just any function whatsoever. It could be possibly just x, in which case limit law 11 and limit law 10 are saying the same thing. But if our function is x plus 1 or 4x plus 1, f of x is now just a placeholder to say any function whatsoever whose limit exists. Does that make sense with that question there on limit law 11? Yeah, absolutely. Other questions so far?
Would that still work if it was, so would you use limit law 10? Say if x was by itself, but it had a power associated to it, say it was x cubed or x to the 4th, would you be able, in a square root, would you still use limit law 10? Or
limit law 10 still wouldn't be available, but you could force it. You could actually make that work, because if you say have square root, say limit x tends towards 2 of, let's say x squared to keep it kind of contained, then limit law 10 still is off the table because it specifically says just x.
X, okay.
Yeah, but you could use limit law 4. If you see x squared, you know that's really just limit x tends towards 2 of x times x. And even though limit law 4 has an f of x and g of x, nothing said specifically f and g had to be different. They could be the same. They could both be the same exact function. The fact we say f and g just allows for them to be different. So now you have x and x, you can split this up and say, by limit law number 4, take the limit of the square root of x times the limit of square root of x. Maybe some algebra first. Limit as x tends towards 2. The square root of x times x is the root of x times the root of x. So we can use that property of square roots. Then this becomes a limit as x tends towards 2 of square root x times a limit as x tends towards 2 of square root x. And then we just evaluate both of them through. Now, finally, limit law number 10 is in effect. Limit law 10 says if it's just an x, you can throw in the value right here. So 2 goes inside both of them right away. This becomes root 2 times root 2. And then that just becomes a 2 altogether. So really, there's lots of weird stuff going on with all of these limit laws, lots of different things you can make happen. But this is the bigger idea as well that Logan was getting into. If you see an f of x anywhere in the limit law, it can really be any function whatsoever. Other questions or comments at the moment? Okay, well, we've broken this one apart. We have the limit of the numerator divided by the limit of the denominator. We used limit law number 11 because we had some generic function, not just x itself. Then finally, down here, all we're doing is just a bit of algebra. We have 12 divided by 4 times 2 plus 1 is 9, so this is square root 9. That means that's 12 divided by 3. And so the whole result is just 4 altogether. So we did it. We cited limit laws as we worked through this. But part of our goal in these notes and the next section of continuity is to observe. We can sometimes do this a little bit faster. All we're really doing is trying to absorb these limit laws, get a feel for what's allowed, what can we take for granted as we do more and more limits. Well, we're going to practice just another set of limits to see how they go, done just a little bit more quickly. But any questions or comments at the moment? Okay, well, let's turn to this last example for the notes. There's a lot going on in these. We're going to look into several problems. I'll hide them and let's consider them one at a time. I'll come back to this remark, use correct limit notation for credit on all assignments and exams, and say specifically what we mean as we look into this problem here for correct limit notation. More in effect on example 3 than the prior one. Now when we look into this one, let's pull up our handy dandy list of limit laws. Nice thing about this function is this is a rational function. All a rational function is, for the sake of review, is a function whose numerator is a polynomial, that's degree 1, and whose denominator is also a polynomial, that one is of degree 2, a quadratic. So because it's a rational function, if a, -3 in this problem, where x is heading towards, is in the domain, our work is done. But notice this slight tragedy algebraically with this one. If you plug -3 inside that denominator, you get 5 times -3 squared plus 18 times -3 plus 9, but that's 0. That means -3 is not in the domain of this rational function whatsoever. So we have to do something else to this to make this work out. So here's what we're going to do next. First, let's make a comment. -3, not in domain. Limit law, I believe that's 14. Yes. Cannot be used. So here's where we go on a bit of an algebraic adventure. We need to change out this function. So we're going to say that this is equal to limit as x tends towards -3 of, let's keep x plus 3 up above, divide this by refactoring the denominator. So I'll start with the 5x, and let me space this out a little bit better. And an x, positive with positive means the signs in the middle have to be both positive. I want to put a +3 here and just hope for the best. If there's a 3 there, and we're trying to get a 9, we should have a 3 here. Here's my check I usually run through. 5x times 3 is going to be 15x. Plus 3x will give us the middle term 18x. So that tells us the factorization is complete on this one. Here's where we do something that's even weirder. This goes back to, I think, section 2.2. Let's pull this up just really briefly. If I can get these windows to fit, bear with me for a moment. Here, we had some interesting functions like x squared minus 1, x plus 1. We mentioned sometimes you can simplify these functions, but calling them straight out equal is a bit of a lie. They're only going to be equal. In this case right here, if x is not equal to 1, this becomes relevant to us. The functions from the far left to the far right were equal for all other values, and we can observe that on the graphs above. The only difference between those two functions was that one dot here, the loss of continuity, and the fact that it's filled in here on the very far right when we were looking into that example. So these were some strange functions, and we're about to do something very, very similar. We're going to cancel x plus 3. We get another function, limit as x tends towards -3 of 1 over 5x plus 3. But that's not the same function as the one over here in green, in blue, as the one over here on the far right in green. These are actually different functions. They agree everywhere except at -3. That's where the difference is between the two functions. So we need something to kind of rationalize this. We didn't do anything unusual algebraically. In ordinary algebra, we cancel things. But if we were to plot both these functions, it's the same sort of situation as what we saw over here. One of them has a hole in the graph, the other one doesn't, this time at -3. They're actually different as functions. But this is where limit law number 13 is tremendous for us. Let's just screenshot this in to kind of highlight its importance. This is one of our major tricks. We have two functions, an f of x and a g of x. They're equal to when x is not equal to -3. But at -3, they're actually different. The one on the left is undefined. The one on the right is defined at -3. But if they're always equal, except for that one point where the limit is heading towards, then the limit for the one of g exists and is equal to the one for f. These limits are in fact the same. So we can switch out this function by reducing it and not change the value of the limit. And now once we get here, the direct substitution property is in effect because this is now a rational function. What's even better is -3 is in the domain of that. Substitute it in, and you don't divide by 0. So this property says for rational functions and polynomials, take the value x tends towards a, -3 in our problem, and just throw it in the function, whether you call it a f or a g function. So this turns into 1 over 5 times -3. My 3's are looking kind of funny. Let me fix that one. Plus 3. So once we swap the function, we closed out the discontinuity, we can use the direct substitution property, plug in the number, and get a value out. So this is now equal to 1 over, that's -15 plus 3, so -12. So the limit of this function as x gets closer and closer to -3 is nothing but a -1/12. Kind of weird in a way. Any questions at all, folks, with the use of those two limit laws? Okay, well, let's give another comment on this one because sometimes seeing is believing. if the limit of the function in blue is really negative 1/12, let's put that number down. What that would mean is as x gets closer and closer to -3 for that function, the output of the function is getting closer and closer to that repeating decimal. So let's put that to the test. Let's plot y equals x plus 3, 5x squared, plus 18x plus 9. We're concerned about -3. Once again, observe at -3, there is a hole undefined. The function in green is exactly the same, but it fills in that one hole. But if we're very, very close to -3, look at the second coordinate. That's the function values. -0.8696 is pretty close to -0.0833 repeating, which is the -1/12. We zoom in more and more and get closer and closer from either side. We can make this as close to -0.0833 repeating as we want, just by getting closer and closer to -3. So even though this work looks kind of strange in a certain sense, it's abstract, this is what it's saying altogether. The function in blue, undefined at -3, but as we get closer and closer to -3, this function is heading towards getting closer and closer to -1/12 altogether. Well, that's really the major limit laws in a nutshell. Limit laws number 13 and 14 are extremely powerful. We're going to be using and abusing them on the next problems. Any questions or thoughts at the moment? Okay, I want to come also back as a promise to this remark of using correct limit notation for full credit. So this applies to homework assignments, to exam assignments as well. Correct limit notation means we have to copy down the limit sign as we go. Once we do the evaluation, we drop the limit sign right at this stage, and we're just computing out a number. But the major thing that I'm really looking towards is in correct limit notation is this statement. We cannot say x plus 3 over 5x squared plus 18x plus 9 is -1/12. That statement there is a bold-faced lie because the thing on the left is a function. It varies. Its values change depending on what input value you put in. This curve doesn't represent -1/12 altogether. So when I say correct limit notation is expected, what I mean is we must is always a strong word, say, what we mean is that the limit as x tends towards -3 of x plus 3 over 5x squared plus 18x plus 9, that is the quantity that's equal to -1/12. So the limit statement right here is what makes this equation true. So don't forget the limit statement is the major takeaway from the use correct limit notation remark here in the notes, also duplicated in the homework exercises. Well, that's one limit down, part A. We're going to look into several others. Any questions or comments at the moment? Okay, well, so far as evaluating limits goes, the other major thing we did in part A was really just a bit of algebra. So this is kind of a nice section in the sense that we're doing a lot of algebraic review. And there's some decent review problems we're going to take a look into in the next set. The first one was really just reviewing factoring. That's what made this problem break apart and get solved in a reasonable way. As far as this one goes, there's no way I could come up with a creative way to factor that's going to help us do the limit. We might try direct substitution in some way, but we don't have a rational function. And we can't plug in 0 down below either. We have a 0 in the denominator, and so essentially anything can happen. This one had a 0 in the denominator, but the limit did exist. It's -1/12. So this one's a little bit trickier in a certain sense. If you see square roots come up in this kind of way, the major idea for this one is use a conjugate. Let me try to get some space here a little bit better. There we go. So the trick to getting through this one is to multiply by the conjugate. We'll review what that means algebraically as we go. If we're doing this kind of limit and we can't plug 0 inside, we convert this to a new limit. Take the limit as x tends towards 0. I'm just copying the original problem, so we know what we originally started with. 1 plus x minus 1 over x. And the conjugate of that thing is going to be taking the root. 1 plus x, we convert to plus 1. 1 plus x plus 1. So this whole fraction is really just multiplying by the fancy number 1. It becomes a conjugate when we swap whatever sign this is from negative to positive in this case. If it was a plus 1 instead, we'd swap to a negative 1. Always looks a little bit worse before it improves. This looks bad at the moment. But conjugates are fantastic because the struggle with this problem is the fact that there's a root inside of this. When we multiply a conjugate by the conjugate, the square root is going to evaporate in this problem. So the next thing we're going to do is expand. We're going to take the limit, x tends towards 0. And if you've expanded conjugates before, you're probably already done just taking a look at it. The middle two terms will always cancel. But for the sake of a paper trail in the notes, let me just show what this looks like algebraically if we multiplied it in full. Using the FOIL method and expanding, a root times the same identical root annihilates the square root sign, and we just get 1 plus x, the radicand. Then we distribute, multiply here to here. That's times 1, so we just get plus root 1 plus x. Now we're distributing negative 1 into the next group through the FOIL method. This will be minus root 1 plus x. And lastly, we're distributing here to here, negative 1 times positive 1, for just a minus 1. So, as promised, the middle two terms are completely nullified. What we really did is we took a plus b times a minus b, and you get a squared minus b squared. That's the underlying formula when we multiply conjugates. But when you square the first thing, the square root symbol falls off. Squaring this negative 1 is going to just give us 1 itself. I said that weird. Squaring the 1 right here, maintaining the negative sign in the middle, here to here, just gives you the 1. So that's what happens when the dust settles in the numerator. The denominator is tricky as well because we actually want to leave it in its factored form. Just take x times the group root 1 plus x plus 1. Then more cancels here. The 1 and negative 1 nullify each other. And we have a much more simplified function. Now this is equal to the limit as x tends towards 0 of just x in the numerator divided by x times the root 1 plus x plus 1. So we haven't really changed it a whole lot, right? We started with something pretty complicated as a function with that root there. But once we get to this stage, there's another cancellation. We can cancel x by x. Those are gone. A 1 here is just a reminder for me that the numerator is still in effect. And now it's a limit as x tends towards 0 of 1 over root 1 plus x plus 1. Almost. It's not quite rational because of the root, but it's going to feel just like a rational when we go to evaluate it. But the major thing that's much improved is, notice if you put a 0 there, you're no longer dividing by 0 like we were in the original right here. That x in that spot is the whole reason this is a complicated limit. But when we multiplied by the conjugate, it eventually just canceled right out. And it boils down to this problem. It's not the same function, but it only differs at one spot when x is 0. So we're using limit law 13. We're not using the direct substitution property directly, and we're not going to break it down as carefully as we did, say, on example 2. Let's just run through the things that we know we can take for granted to show how this goes. So instead of making a mountain out of an anthill in this one, here's how we start taking the limit laws for granted. That's a fraction, so limit law 5 works. We would take the limit of the numerator, but it's a constant. The limit of 1 as x tends towards 0 is still 1. And so 1 just stays right exactly where it is. Then you take the limit of the denominator through limit law number 5. But there's two functions separated by plus. That means you use limit law number 1, take the limit of the first function, that one, plus the limit of the second function, that one. But that's a constant once again. The limit of 1 is just 1. Then we scoot all the way down to limit law number 11. You're taking the limit of that function, which means the limit goes inside. You're taking the limit of 1 plus x, but that's the direct substitution property. It's a polynomial. All you're doing, in fact, is plugging 0 right exactly there. That's what the whole thing boils down to. It's not this direct substitution property, but we're, in fact, using direct substitution. And that's why we have a whole new section to expand on this called continuity. This function is continuous at x equals 0, is what we'll say later on. And so we're allowed to just plug in 0 right there and get the value of the limit. So the limit laws support this as well, running through them step by step. But we are welcome and encouraged at this point of the notes to take them for granted. We'll plug a 0 there, get 1 over root 1 plus 0 plus 1. Notice we drop the limit statements right at this stage because we've now substituted a value for x. X's are gone. And now that's just a square root of 1, which is a 1. The whole thing becomes 1 over 1 plus 1. So 1/2 altogether. So that's the tricks for getting through this one. The conjugate was the major thing to navigate the algebraic side. That the limit laws support us in just dropping in a 0 right in that one spot. We didn't divide by 0. We didn't violate anything algebraically. And so that's the right value for our limit. Well, any last questions or thoughts, folks, getting through this one? Okay, again, there's lots going on with the limit laws, but as far as the problems go here on example 3, the thought is, first, if you know it's a rational function, try to directly substitute. If that fails, try factoring. If it's not rational, something like this, try to directly substitute. If you're dividing by 0, when you plug in 0 for x there, try multiplying by the conjugate, simplify it as much as possible, then directly substitute in the 0 once again right at that stage. And then continuing on this theme, here's our next set of problems to take a look into. This time we're taking the limit as t tends towards 0 of 1 over t minus 1 over t squared plus t. These are two rational functions. And sure, limit law number 2 says we might be able to separate these out, but that's only if the limits exists. And if you plug a 0 here for 1 over t, well, that depends on how you approach 0. That's either a positive or negative infinity. That limit doesn't exist at all. But it doesn't mean the whole thing fails to exist. These are some really, really tricky limits. We need to investigate this further. If you're looking into a fraction like this, difference of fractions, the major algebraic technique is not conjugates, it's not factoring. This time the idea is add the fractions. Which means this one just becomes kind of just a major review of algebra dealing with this kind of fraction arithmetic right here. First thing we want to do, if we're going to add the fractions to resolve this limit, is do any factoring you can possibly do. T squared plus t does factor. T is the greatest common factor. So we can rewrite this as the limit t goes to 0 of 1 over, let's make this one a little bit bigger as a denominator, 1 over t with the placeholder there, minus 1 over t times t plus 1. So now that we have that structure, notice that there's a common factor, t on both. There's one factor missing, a t plus 1. We want the least common denominator, but once we have the fully factored form, we can just see what's missing. T plus 1 is missing here, so we just throw it in. Go t plus 1 above and below. Now we've completed the denominators. The least common denominator is t times t plus 1. So all we did is factor out t on the first. When we looked at the two fractions, make them the same, but make sure you're multiplying and dividing by the same thing. So that we had to cancel and go backwards, we're back to the original function. In other words, we can't damage that equality there. It has to be maintained. So that's our new function. We can now subtract across the numerator. We'll call this the limit as t goes to 0 of t divided by t plus 1. Excuse me, I said that weird. Something over t times t plus 1. And the numerator of 1 times t plus 1 is just t plus 1. Then go minus 1. So we'll have to do this kind of work here and there. There's a problem like this in the homework assignment as well. Just a good review on algebra, getting through this kind of problem. Simplifies further with that like term. This becomes limit as t goes to 0 of t over t times t plus 1. So we started off with two rational functions. We could not use the direct substitution property on those rational functions because that 0 there is not in domain of 1 over t, neither 1 over t squared plus t. So can't use direct substitution at all. But notice what happens if we just push forward on the algebra. We get to this one, it's still one rational function. Tragically, that 0 is not in the domain of that function, but we can reduce it. Just cancel off the greatest common factor, numerator to denominator. We get limit as t goes to 0. It's a new function, but it only differs on one value, 0. For all of their domain values, the one on the left, the one on the right are identical. So limit law number 13 says we didn't change the limit, we just changed the function. So that we can use the direct substitution property. It's kind of the name of the game. Do some algebra until this shows up and it works because of the property number 13 allows us to get the same value of the limit. So now that one's a rational function. 0 is in domain. So all we do is we take that 0, plug it in for t. Let me fix my penmanship on that arrow though. There, looks like an equal sign. So take this 0, direct substitute in for t, and we get that this is 1 over 0 plus 1, just showing this step for the paper trail, how we do that evaluation. That means this is just a glorified 1 over 1. The whole thing is 1 altogether. That's bizarre, right? These are complicated functions. They don't exist at 0 whatsoever. Yet if you take 1 over t minus 1 over t squared plus t, both these functions are either positive or negative infinity as t goes to 0 from the left or the right. But the difference of them gets closer and closer to 1 exactly. So we're not saying that this is approximately 1 when t is near 0. We're saying that the value of the limit is exactly 1, and we can get as close to 1 as we'd like by making the input variable over here as close to 0 to get as close to 1 as we need to get. Well, I feel like that one's kind of tricky just because of the fractional arithmetic on this one. Any last questions or thoughts getting through this one here? Okay, well, it looks like we have just one last one to take a look into. The limit as h goes to 0 of this interesting mess. And these are kind of tricky problems because they're not necessarily sorted from easy to hard. These are pretty mixed up. That can happen in our own textbook. It's not always, say, an easy problem following a hard one algebraically. Adding the fractions is a good amount of work. Knowing to use a conjugate sometimes takes a little bit of staring at the function and thinking about it to recall, oh, the conjugate could work. Factoring can be tricky depending on the problem. But on this one, the only really major thing we need to do algebraically is just expand. -5 plus h. -5 plus h is the result of -5 plus h squared. If we expand that, start to simplify, the hope of hopes is something nice will happen and we'll get a result out. Notice we have to do something algebraically because direct substitution is off the table. We can't plug in 0 for that denominator. It would be undefined. So here's our very first step. Let's FOIL this out. We get limit. As h goes to 0 of 25 minus 5h minus 5h. And if you just said minus 10h altogether, good on you for skipping that step. Then last thing in FOILing this out is plus h squared. Then we've done the expansion. Last part is minus 25. And all of it is divided by h. It simplifies a good amount. The constants here combine and are wiped out. We have like terms, negative 10h altogether. So this is now the limit as h goes to 0. Negative 10h plus h squared all over h. And you can just divide h into both terms as you would like right at this step. I think what the author would typically do in the step-by-step for the reading is just factor h from the numerator. So you could rewrite this as limit h goes to 0, factor h out, leaving behind negative 10 plus h, all divided by h. Then that h cancels, but that's cause for celebration in a certain sense. The only reason this one is taking more time algebraically is because h was tending towards 0. If it was tending towards 1, we would just be plugging in 1 and our job is done. But once we cancel that h, that problem denominator right there, here's what we're left with. A limit as h goes to 0 of negative 10 plus h. In the variable h, which is a weird variable, it's a polynomial function. It's linear of degree 1, so we can directly substitute the value 0 in for h, and our work is done. So we go back here, take 0, plug it in for that value h, we get to negative 10 plus 0. And so the whole result is negative 10 altogether. Which means we did it, folks. That's the conclusion of that last limit there. The original function here, which was a complicated rational function in the variable h, is just getting closer and closer to negative 10 as h gets closer and closer to 0. Well, any last questions or thoughts, folks, getting through this one? Okay, well, this is the conclusion of the limit law section. I feel like sections 2.2, 2.3, they're kind of intense because limits are new, and we have a lot to discuss when we describe a new process like taking a limit. But part D, with the weird variable h, it was kind of relevant to section 2.1. This is our ultimate goal in this section, and we've turned to this page of notes once, a couple times already. We'll do so more as we go. But that h is kind of like the h that you see here on these notes. In the weirdest way ever, and we'll come back to this when we're further on in chapter 2, but in the weirdest way ever, this process right here, that one limit as h goes to 0, is very similar to that h right here when we looked at a plus h and getting that secant line. These are the type of limits that emerge when we find the actual slope of the tangent line. which becomes the concept of computing the derivative of a function. These are the limits that we encounter, and computing a derivative is just coming up with some slope, which could represent anything. We looked at a velocity as an application in that section, 2.1. So even though this feels kind of disconnected from reality, this comes back to computing a slope, which could be really any kind of physical quantity whatsoever. So with that in mind, let's close out this section and now go and take a look into the continuity section. We'll take a decent chunk out of this section. It's kind of a shorter one, but we'll probably not try to race through it today. Finish it off when we come back on our Thursday's class before getting into section 2.6, limits at infinity. Okay, so now in the continuity section, one thing I want to say right away before we delve too far into continuity is what our ultimate goal is for continuity. We go back to the limit laws, and the direct substitution property was the major superstar that made a lot of our limits really, really easy to compute at the last steps. We want to expand on the direct substitution property. It turns out it's not just polynomials and rational functions that have this property. There's a wider class of functions where they work on, and that category of functions are called the continuous functions. And if you recall from the very first class meeting, calculus really has three major domains: continuity, differentiability, and integrability. So we're delving into one of the major parts of calculus, continuity itself. Continuity allows us to do limits just like that. In fact, let's put these together. Let's read the definition of continuity. A function f is continuous at a number a. Italics a because it's the algebraic ID, the mathematical symbol. F is continuous at a if the limit as x tends towards a of f of x is f of a. That's the same exact limit. So continuity is really just direct substitution in a nutshell. If f is not continuous at a number a, then we say f is discontinuous at a. That should be italics. At that number a. So that's what continuity is in a nutshell. I feel like I should put that in red because that is a revision. A meaning the number a right here in the limit. So to get a feel for this, continuity, even though it's a fast statement to write down, there's a lot going on with it. It has its own section overall. So here's what the white space is for. I want to draw one function that has a point of continuity and a discontinuity as well. So here's the function we'll take a look into. I'll put it down a point at -4. It'll look about like that. That point is going to be at height 2. I'm going to redefine the function to be at height 1, and the curve comes through like this. So we've seen this kind of situation happen before, actually quite a lot in section 2.2. Then over to the right at +3, I'm just going to put a solid dot, say at height 1. Just seems like a convenient point to put it in. And let the curve come through just like that. Now really that solid dot here at 3, it serves no purpose. It's just some part of the curve that we're focusing on. That solid dot serves a major purpose, and so does that open circle there. It says there's a hole in the graph, and the function's been redefined to have height 1 at -4. So here's another way to think about continuity. Continuity means you're able to draw your curve without having any jumps, holes, breaks, vertical asymptotes that ever emerged. But when I drew this graph, I had to lift up my pencil to actually redefine the function, and that means it's a discontinuity. For the rest of the points, as I draw it out, you would never have to lift up your pen or pencil, and so intuitively that means we're continuous. So let's focus on the continuous portion first. We have that f of 3, where here f of 3 equals 1. The limit as x tends towards 3 of f of x, that's where the curve is heading towards, but as you get closer and closer to 3, the values are getting closer and closer to 1. There's no tricks here. That means limit as x tends towards 3 of f of x is f of 3, and that's what this property up here is saying. You could take this value, directly substitute it into the function, and we were allowed to do that here. So we can say, therefore, a little triangle is for a shorthand of therefore, f is continuous. I'll often use CONT as a shorthand for continuous, especially if I'm running out of paper space, is continuous at x equals 3. The function value and the limit are identical. So whenever that happens, this is what it looks like on paper. And in terms of a limit, that's the whole equation for continuity. Well, that's where it goes right. That's where we have continuity. It's continuous everywhere else on the curve. We were just focusing on the 1.3, except for -4. It's not continuous there. So what goes wrong? If we go in the same order, f at -4 is at height 1. It drops below. That's where it's defined. Yet if we take the limit as x tends towards -4 of f of x, this is a double-sided limit. So on the left, we're getting closer and closer to a height of 2. On the right, we're getting closer and closer to a height of 2. It comes out as a 2. But then that means the values are different. We have that the limit as x tends towards -4 of f of x is not equal to, so put a big angry slash through there to say not equals, f at, kind of squeezing that in. Let me try to economize on my space better, is not equal to f at -4. Continuity means the limits were equal, so we get to say, therefore, f is discontinuous at x equals -4. The limits tell the story. If the limits are different, even by a little, doesn't matter how small the difference is, we have not equals here, and that's a discontinuity. If the limit is the same as the function value, if these come out to be the same exact things, then that's what continuity is, and this is what it looks like on paper. A nice, connected, unbroken graph, no holes, nothing crazy going on. So that's continuity. This gets tricky because we also have the notion of continuity from the left and continuity from the right. But before we delve into this topic below, any questions with the overall arching idea, just continuity itself? Okay, well, let's do another diagram for these because left-hand limits, right-hand limits, they were the tricky part in section 2.2 in my opinion. Now we're combining that with continuity, but notice what the carryover is. It's the same exact equation as in definition 1. The only difference is whether we're putting a plus or a minus for where x is tending towards on A. So if there's a plus, that means x is heading towards A from the right. X is bigger than A. If there's a minus, that means x is heading towards A from the left. That means x is strictly less than A. So think of the plus here, meaning continues from the right. Let me highlight that a little bit better. It's more about that plus. And the minus right here is meaning we're dealing with continuous from the left. Visually, this is what it's going to look like. So I'm going to draw a more complicated looking graph. I want to start with a point at -2, put down a solid dot and an open dot at heights 1 and 2. Then 1, 2, 3. Let's put in some negatives just for the sake of variety here. I want to put down a solid dot at -2 and open dot at -3. And here's what my curve is going to look like next. So I want to, let's see here, want to make this come out just right. So I want to make the curve come in to a solid dot like that. Then from the open dot to the open dot. And then leave the final solid dot from the right going in any particular direction. Let's make it look linear this time. So there's the curve. It's just one overall function. We can call it y equals f of x to emphasize. And it has kind of a lot going on with it. I'm interested at what's going on at -2, what's going on at +3. We're going to see if at those numbers, the curve is continuous from the left, the right. Well, I said that with the wrong inflection, continuous from the left or from the right. Best way to analyze this is just take some limits. So this is kind of a review of section 2.2. At -2, we can take the limit. X tends towards 2 from the right. Limit as x tends towards 2 from the left of f of x. And we also want the function value, f at -2 itself. Sorry, I made a typo there. I should have said -2. Let me fix that on the limits. X tends towards -2 from the right. That's a lot of symbols. X tends towards -2 from the left. So I omitted those negative signs there. Sorry for the distraction on those. It needs to be that -2. So we have three different things to evaluate here as we run through this. F at -2, the function value is the fast one. That one it's meant to be exactly height 1. Now, if we look at this one, let's go from bottom up. This is x tends towards 2 from the left, meaning x is less than -2 rather. So we're following this curve, and as we go along this curve, it goes up. Looks like it peaks out here, then starts to go down, getting closer and closer to a height of 1 again. We take the limit as we head towards -2 from the right. We're on this piece of curve, getting closer and closer to -2. We're reaching a height of +2. But what we're looking for is equality. Equality happens on these two. It emerges with a negative there. So since we have those two limits coming out as equal, that equation holds, and we can say, therefore, f is continuous from the left at x equals -2, only because these were the only two that matched. If this value here came out as a 2, it would have matched with the top limit. We would have said something different, continuous from the right. So if we move left to right and we land on a solid dot, that's continuous from the left. It's a shorthand way to think about this one. Then we move along the curve, we end on an open dot. Well, this one doesn't look like continuous from the left. It didn't do the same thing as the last one, but the only way to really know for sure is to track these definitions again. So we're going to do 3 more evaluations, 2 which are limits. But any questions at all first with this first batch? Okay, well, let's try it out all over again. If we're here at the next point, 3, there are 3 interesting things to take a look into. They are going to be, like before, limit as x tends towards 3. Well, limit as x tends towards 3 doesn't exist because its values depend on the direction you come in. Let's keep the order the same and say we come in from the right. So put in a plus. For f of x, we want to look into the limit as x tends towards 3, coming in from the left for f of x. And finally, the function value, f at 3 itself. So 3 things to evaluate. For f of 3, we go to where the solid dot is. It's at height 2. So that one's done. Next, when we head towards 3 from the left, this limit here, the one in the middle, we're going down this curve. The function's heading towards a height of -3. And I think I messed up my values here. Sorry for the distraction. That is not quite 2, is it? That should have been a -2. Sorry for the negative signs on this. So f at 3 is down 1, down 2. So -2, that's a silly mistake to make. I noticed it only when I picked up that negative sign there. Now, one more limit. If we head towards 3, but only from the right, that means we're taking values of x strictly bigger than 3 through that inequality here. We're following this curve. It's getting lower and lower, getting closer and closer to a height of -2. But this time, the things that match up are the top one and the bottom one. The limit only comes equal to the function value when we look into the right-hand limit. So from here to here, we can say that f, let's say therefore, f is continuous from the right at x equals 3. Well, we did it, folks. That's the punchline of continuous from the right versus continuous from the left. It's tricky because now it's using single-side limits as well to define continuity, but really it's just extending beyond original continuity, which is a double-sided limit. So these limits had to exist, come up to the same value on either side. But when we have these jumps, which we'll later call jump discontinuities, we lose continuity here truly, but we retain a slight amount of continuity. This came in as continuous from the left. This came in as continuous from the right. Any last questions or thoughts getting through this one? Okay, it's, in my opinion, quite tricky to analyze these by breaking down 2 potential limits and 1 potential function value and matching them up. So here's where the graph is really, really powerful. The more you stare at this, the more you're going to notice there is a dead-on, honest pattern with these types of single-sided continuity. Yes, that's correct, Caleb. We're skipping from section 2.4 into section 2.5. Section 2.4 is about the precise definition of the limit. It's a good section, but we're considering that section optional. Other questions at the moment? Okay, so the last takeaway from this one is the reason we have continuous from the left at the -2, you can see by visual inspection. Let's say, make a quick comment here. Moving left to right on this curve lands on a solid dot. This means continuous from the left. So that's the whole punchline. If you're on this curve and you moved left to right, and you do in fact land on a solid dot, that is the essence of continuous from the left as a visual graph. And if you turn it around, if you're on this portion right here and you're moving from right to left, landing on a solid dot, that's the essence of continuous from the right. So if you go from right to left, land on a solid dot, you have continuous from the right. The other thing is you're always landing on a solid dot. If you do not land on a solid dot, say if I take this right to left, that's an open dot, no continuity. Left to right, open dot, no continuity. Here I'm going left to right, landing on solid, that's continuous from the right, continuous from the left. Here I'm going right to left, landing on a solid dot, that's continuous from the right. So landing on a solid dot is also an important part of the essence. And it's kind of a really just a pot shot of which method you prefer if you're looking at a graph. Some people prefer writing out those three expressions, two limits and evaluation. Some people think in terms more geometrically, like these two ideas here. I'd say it's a good idea to try to internalize both of them, see how they work. And that gives you kind of an extra internal check as you do these sort of problems. So these are the major new definitions in this section. We have a little bit more time, so the next question goes, let's see, a little bit faster. So let's make this the last question for the notes before we end the day. But first, any questions at all, folks, with these technical definitions here? Okay, with everything we've done in mind, continuity from the left or the right or double side continuity, here's a messed up looking graph. It's not the world's worst graph, but it is just one function f plotted in blue. Doesn't hurt to highlight that to emphasize. It has a hole, another hole. It has a sharp point, but it doesn't have anything wrong going on with that. It seems to jump down and then it has a vertical asymptote. So all we're doing here is stating the numbers where the graph of f is discontinuous and also saying what kind of discontinuity these are. So starting on the first problem point to moving left to right, imagine again you're drawing this curve, but as you go to draw it, you have to pause here to emphasize there's a hole in the graph. So that's going to be the first discontinuity. We didn't just plot it straight through, we're continuous all the way until we arrive at a hole. Then we keep on plotting. We arrive at another hole. Sure, the function's defined at a different height, but the moment there's a hole in the graph, that's another discontinuity. So the next one is at x equals 2. Here, this is a really sharp point, but there's no problems there. The limit exists. It's the same as the function value, 0 in either case. But when we go up here, that looks like the single-sided continuities we were looking at before. If we're talking about just continuous or not, this one would be a discontinuity. We have to say further if we're talking about continuous from the right or the left. That has to be baked into the instructions. So as you're drawing this out, if you have to lift up your pencil to drop down a new height, that's a discontinuity. X is 4. And here's another major discontinuity. This one is conveyed as being a vertical asymptote. The curve goes up without bound, but that's a true barrier. You can't ever go around like that. It's not an asymptote any longer. You have to lift up your pencil, come over here and draw the next part as it goes down and up as well, approaching the asymptote. So that's the next discontinuity at x is 5. So there are 4 discontinuities altogether, but we also want to categorize them, state the type. Any questions first, folks, with the types of discontinuities we have? Or excuse me, the discontinuities rather. Okay, well, as far as discontinuities at x is 1 and x is 2 go, the name that these have are called the following. Both of them are called a removable. I'll abbreviate discontinuity to DISC for discontinuity. That's kind of a strange term, removable discontinuity. We don't want to remove it, but here's the thought. We go back to section 2.1 for just a moment. Wrong section. If we go back to section 2.2 for just a moment, let me try again. Here it is. I think the computer's getting kind of tired. We looked at two particularly interesting functions, an f of x, x squared minus 1 divided by x minus 1, and h of x, x plus 1. But that's in fact a discontinuity right there. There's a hole in the graph. That's a removable discontinuity. And the reason we call it removable is you do just a little bit of algebra on this function, factor, then cancel. You've removed the discontinuity. You've changed into a function h of x. You've essentially plugged the hole. So a removable discontinuity is essentially this idea. If you move a point up to plug the hole, there's no discontinuity any longer. If you take a hole and redefine it by just plotting a point there, or doing this algebra down below, which is the same exact thing, just analytically, we've removed the discontinuity. So you remove the discontinuity by plugging a hole here and moving that point up there. We don't want to change the curve or leaving it just as is, but you can fix the discontinuity by just making those two corrections. And so that's the reason they're both called removable. Now, x is 4 is not removable in the same kind of way. How would you fix this discontinuity? You would have to take the whole entire curve, and the whole thing has to go up. It means you're moving infinitely many different points all at once to break that curve up here, just so that it can look like this. But if you have to move infinitely many points to remove the fact that there's a discontinuity there, it's no longer called removable any longer. But I think you'll like the name of this one. If we go from a height and either jump down or jump up, it's simply just called a jump discontinuity. I don't know why I didn't use the shorthand this time, but that's the full statement, jump discontinuity. So here we jumped down a height, so we called it a jump altogether. And here's the last one at x equals 5. There's a vertical asymptote there. The limit as x tends towards 5 of f of x is infinity. And because of that, the classification for this one is called an infinite. I'll use the shorthand, disc for discontinuity. And we would call it an infinite discontinuity, whether we got infinity or negative infinity. We'd still call it infinite. So it comes in two flavors, either a positive infinity or minus infinity. Essentially, if you have a vertical asymptote, an infinite discontinuity will occur. Always occurs with vertical asymptotes. So those are the discontinuities. We've seen all of these discontinuities before in the prior sections. All we're doing now is naming the type of discontinuities. There are other kinds, but these are the major ones that we'll see for the purposes of homeworks and exams. If you're curious of just what can go wrong with functions, here's a really cool function just as a reminder that functions are pretty bizarre things. Take a look at this function of y equals, let's make it be cosine, 1 over x. This is one of the more bizarre functions where it has a discontinuity right at 0. But it's not because there's a removable discontinuity. It's not because of a jump. It's not because of an infinite discontinuity. There's no asymptote. The reason the curve y equals cosine 1 over x is discontinuous at x equals 0 is because the period of how the curve oscillates ups and down increases more and more the closer and closer you get to 0. The curve just never settles down. At this level of zoom, Desmos is just breaking down and putting in a solid space here. There is open space, but the curve is moving up and down so fast around zero, it's never settling down on any one number whatsoever. So that's one of the more bizarre kinds of discontinuities. But these are the major ones that you should be prepared for as far as homework comes up and exam questions come up. Be ready to go for these three different kinds. Well, I don't want to rush through part B, so that's why we looked at kind of a strange discontinuity on this one. As a reminder that functions are weird, here's a pretty weird one. When we come back on Thursday's class, we'll review continuity, go and review what we mean by left-hand continuity, right-handed continuity, by finishing up part B and then moving forward in the notes. But before we call it a day today, any last questions or thoughts at all, folks? Okay, well, have a great evening, folks. When we come back, we'll finish off these notes here. We're going to move into doing a sketch problem, look into theorems of continuity, and then we'll be back to just evaluating limits. But because we're using continuity, these will be some of the nicest all-time limits that we've seen so far in the course. Really, the hardest thing about continuity is just defining what it is, getting through all the little nuances. But have a great night, folks. We'll be back to it on Thursday. Thanks. Have a good one.